last class we talked about energy, so the different types of energy, energy stores, the transfer of energy, uh, right, and work. So different kinds of work, measuring energy transfer. So that's basically work. We talk about the formula for work, which is force multiplied by the distance moved in the direction of that force. We did a question or two regarding that. And then we talked about the principle of conservation of energy. Now, continuing with the chapter, we are going to now specifically talk about two of the energy stores, kinetic energy and gravitational potential energy. And along with that, we're going to lead into the conservation of energy. So the principle of conservation of energy, we need to see how that works in objects that are moving. So the conservation of energy between gravitational potential energy and kinetic energy. And from there, we will see that if we have time, we can move on and talk about efficiency and power. So, by the way, the topics that we're currently covering, kinetic energy, gravitational potential energy, and the conservation energy, is part of the extended syllabus for IGCSE. It is part of the whole syllabus for O Level because O Level doesn't have that differentiation. So just keep that in mind. All right.
Okay.
So kinetic energy, right, or otherwise denoted as E K. So what they say is, right, kinetic energy is the energy an object has because of its motion. So, right, an object with mass m, right, traveling with a velocity of v, right, meter per second. And so the formula for kinetic energy again, ek. You don't have to write ek over and over again, but I'm not, I'm writing it so that it becomes clear to you that ek means kinetic energy, and the formula for that is half m v squared, where m is the mass and v is the velocity, right? So, and mass is in kilograms and v is in meter per second. So, right, m kilograms, and right, this value is in joules, which is the SI unit for energy. Now, what they go on to explain is kinetic energy is directly proportional to the square of velocity. So what that means is, right, you can say directly proportional or depends. That's the word they've used, the term they've used in the book. And so what that means is, right, you've got two objects. Object one is traveling at 100 meters per second, and object two is traveling at 1,000 meter per second. Comparing these two objects, how many more times faster is object 2 than object 1? How many more times faster is it? What is the multiplier effect over there?
It's much more.
Well, obviously, but Rhyme, any guesses?
10 times faster.
10 times faster, right? Because 100,000, so 1000 is 100 times 10, so object 2 is 10 times faster than object 1. But because we're talking about v squared, right? Object 2 has 100 times more kinetic energy than object 1. And why is that? Because 10 squared equals to 100. And about 100 times, right? 100 times. It's not just 100 meter per second more. Okay. So if we were to calculate, you know, assuming that the mass of these two is same, let's, for the sake of simplicity, let's say it's 1 kilogram. And so we do the half and we basically what the difference we're getting is we're getting 100 squared, which is 10,000. We're getting 1000 squared, which is a million. Right, and so how many zeros difference do we have over here? We've got 4 zeros here, 6 zeros here. So that's 2 zeros, right? So it's 100 times more kinetic energy. Make sense?
Yeah.
You obviously divide by 2 and whatever, but still the factor
Yeah.
will remain the same.
Yeah.
Okay. Then, right, if you want to do like a simple calculation, right, there is a question. Calculate the kinetic energy of a ball of mass 0.4 kilograms moving with the speed of 80. Right, so you've got mass equals to 0.4 kilograms. Velocity is 80 meter per second. And so EK equals to half into 0.4 into 80 squared. Right, so simply do that. And so what is 80 squared? 8 squared is 64, I believe. So that will give you 6400, right?
Uh, Let me just check.
It will. And so that is 0.2 into 6400. And so,
That will be 1280.
right, and so that will be 1280 joules of kinetic energy.
Yeah.
Simple. That
Yeah.
is, I mean, that's as simple as a calculation you can get from this.
Yeah.
Okay, next up, gravitational potential. And this is EP. So gravitational potential energy is the energy an object has because of its position or condition. Condition. And so generally what we are going to be asked to do is talk about uh, an object that is at a certain height. So, right, an object that is at a certain, so this is the Earth's surface, and this is some object, right? This is how high it is above the surface, and this object obviously has a mass. And because there's gravity involved, right, you've got G as well, right? And so what they go on to explain is the work needed, the work put in, again, right, the physical definition, the physics definition of work, the work put in to raise that object up to a certain height, right? So work done is force into distance moved in direction of the force, right? Force in this case is you are going against the weight. So that is mass into gravity. That will give you the force. And the distance moved is the height. And so, right, we know work done is, right, the capacity, like energy is the capacity to do work. So when object has been raised from the ground up till that height, it has gained potential energy equivalent to the work that has been put in to raise it to that height. And we know that work done and energy are both in joules, right?
Yeah.
So what you have is, right, acha, the H is given as delta H, which is change in height, because in case of work done, we went from 0 up till whatever height you raised it to. And so therefore those three dots, these three dots mean therefore, right, change in gravitational potential energy right, EP delta, because we're going to change, so delta EP equals to mg delta H, okay, where mass is in kilograms, G is Newton per kilogram, right? That's acceleration due to gravity, Newton per kilogram or meter per second square, right? Both are the same. And H is in meters because it's a distance, and the energy is in joules.
Okay.
So, does this make any sense to you?
Yeah.
Right now, we need to put it into practice. Right now, we can't argue as in why is it this way? It is, right? But let's put it into practice. So you're being asked to calculate the gravitational potential energy of a mass of 0.2 kilograms raised to 2 meters. Alright, so you've got the mass is 0.2 kilograms and the height it is raised is 2 meters. Right, and so gravitational potential energy equals to mg h. So you've got 0.2 into what's the value of g? Remember?
Yeah. Wait. I have to go back, I guess.
9.8
Yeah.
into 2. So what do we get? Simple multiplication.
We get 3.92.
3.92.
Yeah.
And so that is the gravitational potential energy of this mass.
Okay.
Correct?
Yeah.
Now, conservation of energy. And to explain that, we are going to talk about, right, both gravitational potential energy and kinetic energy. So the concept of conservation of energy was covered earlier. Let's just go back. Right, the principle of conservation of energy is one of the basic laws of physics, right? Energy cannot be created or destroyed. It is always conserved, means it is always transferred from one store to another, right? That is what you need to keep in mind, including energy lost, right? So heat, physical, mechanical work is done. Energy, chemical energy is converted to heat, it's converted to light, it's converted to sound, maybe, right? Depends on what kind of energy transfer is happening. And so over here, what we're going to talk about is we're going to start off with right, an object that has been raised to a height. If I just put in a diagram over here, this, then right, is an object here and here. Right, it's the same thing, just at two different heights. The object is coming down. Right, so you've got H1 and H2 properly. Right, this is the scenario. Now what they're talking about is, right, energy is conserved. So, right, we're going to talk about an object raised to a certain height, and it is a certain height above the ground. It has gravitational potential energy, right?
Yeah.
Now perhaps you're holding it, it's tied with a string or something. You let it go, so it starts moving towards the ground. And so now it has kinetic energy, right?
Yeah.
Question is, where did that kinetic energy come from? It had gravitational potential energy, now it has kinetic energy. Where did that kinetic energy come from? And so, right, as the object falls, right, it gains speed, which means it gains kinetic energy. Which is coming from the loss of potential energy. Because as it's falling, the height is decreasing.
Yeah.
And so, right, EP is mg delta h. So the lesser the height above the ground, the lesser the potential energy, gravitational potential energy, right?
Yeah.
And ek equals to half mv squared. Now, perhaps we don't know how fast we're going, right? But what we can do is, because it is gaining kinetic energy from the loss of potential energy, and so what we can do is we can equate the two, assuming that, you know, air resistance is negligible and heat, the energy is not lost, right? So we're not taking into consideration heat or sound or anything else. We are considering that the total of the potential energy is being converted into kinetic energy.
Yeah.
And so in this case, what we're going to get is the kinetic energy is coming from the potential. Half mv squared equals to mg delta.
Delta.
Right?
Yeah.
So we're not doing any calculation at the moment, just to explain this. At this point, right? Energy equals to EP. All the energy is potential energy, which is mgh, and ek equals to 0 because it's not moving at this point,
Yeah.
right? And then at this point, right, it has both potential energy, so the energy equals to the gravitational potential energy and the kinetic energy, because it still has gravitational potential energy because it is still some distance above the surface of the earth, above the ground, right?
Yeah.
But it is also moving, so it still has some potential energy. It also has kinetic energy.
Yeah.
And then when it reaches the ground, right, all the energy is kinetic energy because it is at its maximum speed, which is half mv squared, and because it is at the ground, potential energy is 0.
Yeah.
So what this is showing is the conversion, the transfer of energy from potential to, the object having both, to all the potential, gravitational potential energy being transferred and converted into kinetic energy.
Yeah.
Does that make sense?
Yeah.
Now, right, how do we put this into practice? So let's do one of the solved examples, work examples in the book, and to start off by saying there's a boulder of mass 4 kilograms. The mass is 4 kilograms, and it rolls over a cliff, so it is at a height, right? And reaches the beach below with a velocity of 20 meters per second. So the velocity is 20 meters per second, right? The first thing that they're asking you is, right now the wording is important. If I just take you to, if I write it down here, right? It rolls and reaches beach with a velocity of 20 meters. That means that the velocity at the point it has reached the beach, which is the lowest point, it has reached the ground,
Yeah.
right? Which means this is the maximum velocity of the boulder, right? So the first
Yeah.
question is, what is the kinetic potential? What is the kinetic energy? And so we put in that formula, half squared, right, which is half into 4 into 20 squared, which is 400 into 2, which is 800 joules. Right?
Yeah.
Now, right, the second part of the question is, what is, or calculate the gravitational potential energy of the boulder when it was at the top of the cliff. So part B, what is the gravitational potential energy, right, at the top of the cliff? Right, so for that we need, right, gravitational potential energy equals to mg delta h. Now we don't have delta h, do we?
No.
Then how are we going to find this out?
You're gonna make that the subject?
But then we would need the value of potential energy. Do you know what the potential energy was, the gravitational potential?
No.
This is where the conservation comes in. We just calculated kinetic energy, right?
Yeah.
And so we know what its what its energy was at the bottom. And what
Yeah.
we know is all of the gravitational potential energy was converted to kinetic energy when it rolled from the top of the cliff to the bottom, to the beach.
Yeah.
That means that the total gravitational potential energy at the top was 800 joules. Why? Because gravitational potential energy equals to,
Is kinetic energy.
so we know that we know the value of gravitational potential energy is 800 joules at the top of the cliff,
Yeah,
right?
yeah.
Acha. So what they're asking is, yeah. So basically that's all you have to write. Right? Change in potential energy equals to kinetic energy of the boulder as it lands. You put that in words, right? Change in potential energy equals to kinetic energy of boulder when it lands. And so you plug in that and you simply give the value. There's no calculation in this part. It's just concept.
Yeah. Okay.
Here's where the calculation comes in. What is the height of the cliff? Right? So what is delta H? And so now we use, right, NGH 800 equals to, we know the mass is 4 kilograms. We know gravitation, we know the value of G, which is 9.8. And what we need is the height, right? Acha,
You make height the subject?
huh? The height will be
Can
the height will be the subject. So if we just, do that, H equals to EP upon mg, right? So H equals to 800 divided by 4 into 9. Now I'm taking 9.8. They've taken 10, right? So it depends on what the question is specifying. If it's not specifying anything, you can take G as 9.8. If the question is asking you to take G as 10, then you do that.
okay.
Okay? Because
Okay.
we did study that the value of G, acceleration due to gravity, acceleration due to free fall, is 9.8, but it is at times rounded off to be 10.
10. Yeah.
So in this particular question, they've taken 10. I'm taking it as 9.8, right? Or
Which will give us
in fact, to stay on the same page, I'll take 10 as well, right? Which will give us how much?
2000.
2000.
Sorry. Yeah. 2000.
What are you doing?
800 divided by 4
40.
multiplied by
800 divided by
you
40.
have written 4.
4 into 10. Multiplication is happening in the denominator.
Yeah.
So what's 4 into 10?
40. And then
800 divided by 40. Okay, let me do it this way. Cut out a 0. 80 divided by 4.
20.
20 meters is the height of the cliff.
Sorry, my bad.
Alright?
Yeah.
So that is conservation of energy.
And
Now, they mention a pendulum. Have you ever seen a pendulum?
not really.
I'm pretty sure you have. Okay. So a pendulum looks like this. So right, you have a string, and you've got some sort of ball or bob or something attached to it, and it moves left and right.
Oh, yeah. Okay, I have. I think it's mostly in clocks.
Mostly less like what we've seen, but it has other applications,
Yeah.
right? And so it swings both ways.
Yeah.
Now, what they're applying over here as conservation energy, right? This is the highest point it goes to. highest point. Both of these. And that would make this the lowest point. Right?
Yeah.
In the
Yeah.
center. And so based on what we just did, what kind of energy will the pendulum have at its extreme highest point?
Could you say that? Could you repeat that again?
What kind of energy will the pendulum have? So we're talking about a pendulum, right? What kind of energy will a pendulum have at its highest points?
Gravitational potential.
Yes. So at both of these, all the energy is gravitational potential energy, right? And there is no kinetic energy.
So in the lowest, but in the lowest it will be kinetic, right?
Yes, good. So at the lowest point, all the energy will be kinetic energy, which is half mv squared, and there will be technically no gravitational potential energy, right?
Okay.
And that would mean that the pendulum briefly stops. If you've seen a pendulum, it like very briefly, momentarily, like you, I wouldn't say stop, but you could say because it has like no kinetic
Pause.
energy, so it's like sort of pauses at the extreme end and then comes back. So no kinetic energy here, very brief pause. And then when it's passing through the center, it doesn't stop obviously. When it's passing through the center, it has its maximum velocity. I say
Yeah.
velocity because obviously it's moving in a certain direction. So, right, speed
Yeah.
plus direction is velocity. It's a
Yes.
vector.
Yeah.
And then same thing at this highest point, right? So what's happening in between? The same thing that happened with the object we're talking about. At the points in any point in between the center and the extreme, you have both gravitational potential energy and kinetic energy.
Yeah. Okay.
Okay?
Yeah.
And that is basically what they want to explain, right? And so it is a constant shift, right? Now obviously you, right, in clocks and everything, you've got a battery in place, so there's chemical energy over there which is being converted into mechanical energy, which is moving the cogs, which is moving the pendulum, and so that's the energy transfer that's happening over there, right? It is not a system where you get the pendulum moving and just keeps on moving forever. Also, right over here, uh, in this system, right, there is air resistance, and so you will experience uh, energy lost as thermal energy, so as heat, perhaps some as sound, right? In a question, they probably ask you to ignore air resistance so that uh, the calculations you're doing is 100% of gravitational potential energy being transferred to kinetic energy and no energy is lost,
Okay.
right? That detail is given in the book. I just went over it verbally. Any questions so far?
No.
Okay, so we're done with that chapter. The next one is 1.7.2 work, which we've already done in our previous class. So right, that's done. And then 1.7.3, right, which is energy resources. Now, I asked, like you, like Sobia, you weren't there. I did ask
Yeah.
Fatma and Ibrahim to read through this because I'm not going over this because it's just a lot of information about different energy resources, right? So what I will just do is sort of like make a list right over here about the different energy resources they talk about. So putting in the heading over here, energy resources. Then the first thing they talk about is non-renewable energy. right? So an energy resource is obviously something that we can use to get energy from. A non-renewable energy source is
Isn't really much of use, I
no,
guess.
it is something. It is the main energy source that we're using. But the problem with it is once used, it cannot be replaced. So it's used and it's done. It has advantages, right? The advantages, the first one is high energy density, means it has a lot of energy in a relatively small size. And the second one is it's readily available.
Okay.
So the examples will perhaps make this easier to understand. What are the non-renewable energy resources that they've mentioned? They have mentioned fossil fuels, right? So fossil fuels such as oil and coal and gas and all of that. And then they've mentioned nuclear fuels, such as uranium or plutonium. Now, why is that non-renewable? Because once uranium is put into a nuclear reactor and nuclear fission or fusion or whatever is going on happens, the uranium is lost. The energy is given off, the uranium is lost. You cannot get the uranium back. So it's non-renewable, right? And it has like a lot of energy, so very, very high energy density. Right? Details of that is given in the book. Again, right? If you read through it, if there's an issue, you can ask me. I can go over it in one of the next two following classes. But I'm guessing there won't be need. But still, if there is, right, obviously I will cover it. Then they mention renewable energy sources. Renewable energy, right? And so these guys are the ones that are not exhausted, and right are generally not polluting. Generally non-polluting. Examples of renewable energy are solar energy, wind, and what else do we have? Wave energy, geothermal, what else do we have? We've got wave energy, geothermal. Uh, yeah, so those are the four mentioned. Now, right, what they mean by not exhausted, right? So let's take solar energy for example. It's not that, right, the energy that we've got put solar cells and it traps the sunlight and it converts it to electricity and then we use the electricity for whatever purpose. And that doesn't mean that the energy we trapped and using electricity is not going to end. It is stored in batteries, it's going to finish. The reason we call it that we say that it's not exhausted is because it's coming from the sun and the sun is there, right? So unless it explodes, which if that happens we won't be needing energy because we won't be around as well,
Yeah.
right? Unless it explodes, it's there, it's coming out every day, it is shining and we're using the light, and light basically, not the heat. So we're using that light to convert it into electricity, right?
Okay.
And so even
Yeah.
if we use it, we get more of it, right? Without causing pollution and the problems with the fossil fuels and nuclear fuels and all of that. Same for wind, right? Wind is blowing, so you utilize it. You've got waves, you've got waves happening at the sea all the time. make use of it, right? So that's what they mean, that's not exhausted.
When you say that they're generally non-polluting, does it mean there are energies that are polluting as well?
Mm, possibly, right? If they are, let me look that up. That's a good question. Let me look that up. Okay, so just a quick search, and what I get is, for example, geothermal energy is one of the ones that I mentioned, right? Uh, can you hear me?
Yes, sir.
Yeah. So geothermal energy is one of the ones mentioned as, right, found like the renewable energy. So what it says over here is it's clean, but geothermal plants can sometimes release greenhouse gases like hydrogen sulfide from underground reservoirs, and right, there can be impacts on local water and land. So there are side effects nonetheless, right? But then, right, generally non-polluting means that perhaps, right, the side effects are not as widespread and severe as when you compared them to, you know, non-renewable energy sources. Okay.
Okay.
All right. So that was a good question. Right. Then they talk about where there's text. Okay. Then talk about power stations, right? And how electricity is produced at power stations using non-renewable sources and, right, renewable sources. And then the economic, environmental, and social issues over this. Again, that's not to do so much with science. So again, right, read it. If there's still a confusion, anything you want cleared up, you can ask. Otherwise, I'm giving that to you. And so then we come to, right, efficiency of energy transfer. So that will be the last topic for today. And right, let me put it in the heading: efficiency of energy.
Just to let you know, we have 15 minutes left.
Efficiency of energy transfers. So, right, the efficiency of any device, or in case of energy, is the percentage of energy supplied to it that is usefully transferred. So basically, right, uh, useful energy transferred, right, versus how much energy was actually put in, energy input. That is what efficiency is. So to put that as uh, an equation, efficiency, right, it's normally given as a percentage. Efficiency percentage is useful energy output divided by total energy input multiplied by 100. Another way this can be done, right, if you're not dealing with energy but you're dealing with work done, so, right, efficiency percentage equals to work done
Mhm.
Now, right, to explain this, they're referring to right the lever shown in figure 1.5.26. So let me just close it down, clear that on screen. One point five point two six. Put that on screen. All right, remember this topic? Turning effect
Yeah,
of forces,
yeah.
right? And so you've got right a lever, right, and you're putting in effort, and there's a load that you're moving, right? So there's the load, the effort, and so that is the scenario of a lever, right?
Yeah.
So that is the scenario they're referring to. In this case, skipping ahead, right? Efficiency is work done on load divided by work done by effort.
Okay.
So I'll just write that down on the whiteboard. So efficiency percentage is work done on load divided by work done by effort into 100, and this applies to levers. Then another way of doing this, efficiency percentage. If you're talking about power is something we'll do tomorrow. But right, if you're talking about power, then right, it is useful power output upon total power input. Multiplied by 100. You can see the approach is the same. It's just what information or what values you have for efficiency. Do you have the values of work? Do you have the values of energy? Or do you have the values of power? Right?
Yes, sir.
So it depends. Now, right, let's just do a question to understand this. And again, right, we'll come to power tomorrow and then move ahead from there. In fact, you know, it's like really short. In fact, you know what?
What?
Let's do it right now because it's
Okay.
super short. So what is power? Power is the work done per unit time, right?
Can we cover it in 10 minutes?
Yep.
Yeah. Okay.
Work done in unit time per unit time, or energy transferred per unit time.
Just a question, sir. In the efficient of energy transport,
Mm.
the first and last equation, it's the same thing, isn't it?
Okay. Right. The first one's talking about energy, the second one's talking about work, the third one's talking about power.
Uh,
Technically, they're all the same.
okay.
It just depends on what you have to work with. Are you talking about the efficiency of the energy, the efficiency of the work, or the efficiency of the power?
Okay. Yeah.
Okay, so right, the more powerful and a machine is, right, the more work it can do within a certain time period, or the more energy it can transfer within a certain time period. Okay, so it
Okay.
is basically the rate at which work is done or energy is transferred. The formula for this, as you can imagine, right, is power equals to work done on time equals to energy transferred over time, or time taken for work to be done or for energy to be transferred. So in that case, I need to move on to the next page. So P for power equals to either work W over T or energy transferred over T. Okay.
Yeah.
And so, right, the unit is watt, given by W, capital W. So how many watts? You might see this, right? You've got like a 20-watt bulb in your room. That means it's right. That's the power rating of your bulb. Okay.
Yeah.
So, right, 1 watt is means that, right, it is utilizing 1 joule per second.
Okay.
One per second, 1 joule per second. Okay. So a simple example for this is, right, if a machine does 500 joules of work in 10 seconds, right, what is the power? So P equals to, right, work upon time equals to 500 upon 10, right, which comes up to 50 watts.
Yeah.
Simple.
Yeah.
Now, right, coming back to efficiency, let's just do a calculation for efficiency very quickly and we'll be done. So, right, the energy input to an electric motor is 400 joules when raising a load of 200 newtons through a vertical distance of 1.5 meters. Calculate the efficiency. Okay. So, energy input is 400 joules. What's the work done over here? Right, it has moved a 200 Newton load a distance of 1.5 meters. So first thing you need to know, calculate, right, the work done is, right, the energy that is utilized. So first we calculate, oh, how much did we actually use? So work done is 200 into 1.5 is 300 joules. right? So that is how much we actually used, and that is how much we put in. And so simply put, right, efficiency is useful output over total input. I'm being casual about this, right? It's useful energy output over total energy input. So useful output is 300 joules, total input is 400 joules. So right, and into 100. So it's a percentage. You don't have an SI unit going in here, and so that would give you 75% efficiency.
Yeah.
Right?
Yeah.
Simple enough.
Yeah.
And that brings us to the end of class, and we've covered quite a bit. I think we've covered good ground today. So
Yeah.
we're done with 1.7, and the next class we will begin. I don't know whether we'll be able to complete it, but we'll begin with 1.8, which is pressure, and that is actually the last topic of unit 1. Right, so see you guys next class, inshallah.